So to understand how the energy levels are filled with electrons, some more experiments were made to study the energy required to kick the electrons out of the energy level, or the atom. And this is kind of interesting thing, because they called it later the ionization energy. And as I just said, the energy that is needed to move or remove the electron, or the outermost electron, from the atom. And of course, the atoms will have more than one electron, so you'll have first ionization potential, second, third, fourth, or up to the last electron in the atom. So we'd expect that the energy needed to kick one electron is gonna be less than the energy needed to kick the second, and less than the fourth, because as you move one electron out of the nucleus, so the attraction force between the nucleus and the rest of the electrons is gonna be more, so you need more energy than you needed in the first time, so you can move the second. And this is what we see here. If you calculate the ionization energy for one potassium, or the first ionization energy for potassium atom, it's going to be 418. The second ionization is going to be 3070 kilojoule per mole, which is kind of 9 times the first ionization energy. And this is something that is very predictable. So for instance, let's talk about the sodium as an example, and then we will see how the ionization energy helped us understand the electron filling the energy levels. So what we see here is the tabulated data for the ionization energy, the first, second, third, fourth, and then the sometimes it's called ionization potential. That's why it's called here IP. It's ionization potential. So if you read it or find it in different references as energy or potential, it's the same thing. And we'll see here the numbers. The first is 400, the second is 6,000, the third is 7,900, and the 11th one is 177,000. And you'd see that this is almost how much is like 1,000 times more the first ionization energy. If you plot this, you'd see that the data are not very clear. They're not easy to understand. And this is because we have a very, very huge difference in the values between the first and the last ionization energy. And that's why the first few numbers look kind of the same. And as I have the very, very big scale, so the values between 0 and 20,000, which is all these numbers till here, are just squeezed in this part, so that the scale can reach to the maximum point. Now, this is a problem that we face a lot in our applications in engineering, or whatever other application that we're plotting data in. And in this case, we tend to use another kind of plot, which is called the log scale. It's another scale, and in the log scale, I put the powers. So it's 10 power 0, 10 power 1, 10 power 2, 10 power 3. So we can see the increase in the orders of magnitude easily here. And in the same time, I can see that the difference between 100 and 1000 is like the difference between 1000 and 10,000, and this makes it easy for us to see the numbers. And as you see here in this plot, there is I can easily tell that there is a jump between the first and the second, and I can see a jump between the third and the fourth. I mean the ninth and the 10th. And I can see that there is kind of some sort of linear change between the second and the ninth. There's a change, of course, or an increase, but it's not a huge increase. And there is kind of an increase here between 10 and 11, which is not a big jump. And by seeing this, we kind of saw that we have close energies of the electrons here, close energies of the electrons here, and there is a very big difference between this group and this group, and big difference between this group and this group. And we can see the same for the potassium. You'd see that the potassium, we have a very big jump between the first and the second, and they have also 8. And then a big jump, we have the 8, and then a big jump, and then 2 electrons, and this is what we call the energy levels, and this we can see clearly that the energy level we have here, the very first energy level is filled with 2, the second is filled with 8, the third is filled with 8, and then the fourth starts with 1, and this is how the energy levels are filled. So by tracking the electrons filling, or I mean the different elements and the ionization energies of the elements that have more and more electrons, we can tell how many electrons are there in each energy level. So for all of them, the maximum or the largest two values were for the last two electrons, and they're only also they're always 2 in all the cases, which means that the first energy level is filled with 2. Keep in mind that we're going from the last to the first, so this is the first 2 electrons in the or the closest 2 electrons to the nucleus. The second energy level is always filled with 8 electrons. You can tell that these are the 8 electrons in the second energy level. The third is always filled with 8. We have this 8 common in all the energy levels. And from this we could tell that we know how many electrons can fill each energy level. Of course, these experiments were done for a big number of elements, and the reproducibility of the results confirmed this observation. So this is one very important observation, that we could tell how many energy levels are or how many electrons fill each energy level. And then the second thing was when we plot the first ionization energy for all the for the elements that we know. So this is the first ionization potential of hydrogen, this is the first for helium, this is the first for lithium, and so on. Again, it's very interesting to see that there is an increase in a peak in the first ionization energy for some elements, and there is kind of trend here. You can see that helium is the maximum, and then there is a very big drop in the ionization energy, and then it increases till it reaches neon. There is a huge drop in the ionization energy. It increases again to argon, and then there is a huge decrease. So there is kind of trend here. We can see that the ionization energies increases as the electrons increase till it reaches one point, which is when the energy level is saturated. So we know that the first ionization or the first energy level is filled with 2 electrons. It's easy to remove it from hydrogen, but when the energy level is filled, you can hardly remove the electron from there. For lithium it has saturated energy level and one single electron in the second energy level, so it's easy to remove it. It gets more and more difficult till you reach the neon, where the energy level is saturated, and then the same pattern is repeated. So from this we could confirm our results that we got from the previous plots for the ionization energies of one atom or one element to the ionization energies of different elements. And this was a very, very good observation, and we reached the data that we see here. For K energy level, it's filled with 2, and we give it number 1. For the second energy level, which is L, it has 8. For M, it can be filled with 18, and N can be filled with 32, which is 2n squared. So 2 by 1 power 2 is 2, 2 by 8 power 2 is, by 2 power 2 is 8, 2 power 3 power 2 is 18, and so on. I just want you to keep in mind that we saw here that the second energy level here is filled with 8, but I told you here that's filled with 18, and this is something we were gonna discuss when we talk about the periodic table. Just keep it like this, and we will go to this, or maybe before the periodic table. It's gonna be in the next few videos. We'll come to this. So this is how we knew from the ionization energies how the energy levels are filled with electrons. We will go into more details in the next videos, so I'll see you then. Goodbye.